Okay, actually, let me shut down this computer so it's not making noise. Make some noise! We want to go there and close that. And there we go. Sorry about this. Alright. Let that power down. Sweet. Okay, well, I guess it's time to get started. Don't really have anyone watching, so I guess I'll take care of some business, I guess. Started, or not really business, but started working on putting together a course proposal for Egghead based on all the material we've been doing in this live code. So hopefully, as soon as we get to a point where I kind of know where this is going to go, I should be able to finish that up and submit it, and then start recording these. So they'll just be more focused bits around the state monad. So it should be fun. And then I'm working on another bit using a project, or the project that I work on at work. We make e-learning software, so I'm putting together a course for using ADTs in that. So hopefully I'll have that done and available. It's pretty neat. You get to use the product that I build and work with every day. So we'll hopefully get that out to you soon. So I guess we'll just pick up. We've finally got a person watching, yay. So I will start it now. We can stop talking about all that boring stuff. All right. So where we left off last time is we got our pull random to be able to work with our state monad. As we see here, we can delete 2w and we'll just do run with, and we see that this is working with our state monad. We can do eval with or execute with and look at what our state got set to, and we see that it has the seed in the bit. So what we want to work on today is to now get this deck model to actually work with our random number generator that's all hooked up to state. So to do this, we're going to kind of change the flow of what we were doing before. So here we were shuffling all the cards, and we were, allowing them to give you a shuffled set of cards that you can do whatever you want with, right? So now that we're going to be inside of a state, we are going to be namespaced to a specific deck. So really, if we were to keep this structure, we'd either have to implement a zipper, and we don't really have a call for like keeping track of discarded cards. So there's really no reason to implement a zipper or something at this point anyway. Maybe later that requirement will come in. So really what we want is a way to randomly pick a card from somewhere in the pile and show you that card, right? Or like pick that one card out and have that as a selected card. So we'll still use this kind of format with a pair, but we're going to change out what this left semigroup is. Right now we're doing it with an array, so we can build the arrays up on each other. So we can pretty much just shuffle the entire deck. But we don't really need to do that, like I was saying. All we need to do is when we pick a card, we just need to grab it from a random location. So we're going to change this around a bit. And to do this, we are no longer going to be generating our random card here, right? We are going to be, we need this index provided for us so we can pick our card. So I guess let's clear out our workbench here. And we'll use our workbench to build this out. So we don't really need to bring pull random in. We can get rid of all of this. So we'll just get rid of that. We're not really in the state right now, so we will get rid of that as well. Some of the helpers I guess we want to keep, because we'll just rebuild this file over here in our workbench, is we probably want to keep this deck, except we're probably going to change that. Yeah, Yeah, we're probably going to change that. So let's just bring in dec for now. So we'll do const, and then we'll bring in dec, and we'll make dec equal to require, and we'll pull out the good old model dec. Model dec. And let's see what that gets us. So if we look at dec here, we see that we should get back our array of just our cards that we were expecting there. All right, so we'll play with that dec, and let's redo this pick card function. But we're going to do it instead of pick card, let's go ahead and make it select card, right? So, or not select card, draw card, because it's more we're drawing a card from somewhere in the thing. So we'll call it draw card. All right, so we'll do our draw card here, and we'll define draw card as a function that will take, well, what do we need to take here? We need to take an integer for sure for the index, right? And actually, before we do that, let's actually just, we could change around this pick card. We'll rename it later, right? There's no reason in rebuilding all that. We'll just reuse this. So we'll still call it pick card, but instead of bringing in cards and generating the index there, we need to actually bring in our index itself. So let's go ahead and we'll do IDX here and then CS for our cards. And we'll just keep that the same. We need to bring pair in. So let's bring in pair. And anything else we need to bring in? Nope. And this is just the same stuff that we were doing before, except now we can provide the index. Because remember, this index is going to be generated from somewhere else. So we need a way to actually inject the index in. We're going to randomly pick this. We're no longer going to be doing it inside this function, right? So here, let's just do a pick card. And we'll do pick card with an index of 4, I guess. And we'll pass in dec as our CS. Okay, so now we get what we're expecting back. So let's just do a quick little bimap here so we can see what's going on. And on this pair, we want to, let's do display cards. Okay, we'll bring in display cards. That comes in from here. And this is just something that, displays the cards for us. No big whoop. So we'll bimap display cards on that, and we will also do it here. Okay. So now we see that we picked out the 4th card, which of course was the 5 of spades, and notice the 5 of spades is missing there. We could take something like, the 7th or whatever. We'll just replace that with the 7th, and we get the 7th card out. We went ahead and just pulled that right out of there, took that index. We could take the 1st card, I'm sorry, that was the 8th card. So we could take the 1st card and we see we get the 8 of spades. So now we have it to where we can provide the index in and give it a list of cards. So that's pretty cool. But one of the bummers with this is we don't really want this list anymore, because remember, when we call concatenation on a list and when we start chaining this in, because this is all just going to be chained in when we get down to it, the reason why we're using the array here is we're concatenating new elements to it. But that's not really what we want. We don't really want to keep adding new elements to it. We just want to draw one card out and replace it. So that tells us that we're going to need a different semigroup than a list or an array, right? So we're going to need something else. And it just so happens that we have a monoid, which is also a semigroup, or a semigroup called last. And what last does is it's always going to give you the last value that you passed it. So let me show you kind of what that looks like. We will just jump in here. We don't need any of this because we're going to be redoing that anyway. If we were to just take last and we'll say 5, right? So we'll notice this gets us back a last of just 5. Now it is basically just a monoid that's wrapping a maybe, and that allows it, we need to wrap the maybe to be a monoid. We'll get to that in a minute. But if I were to concat in another last, remember like how we were doing with an array, you just keep concating values to it. But with last, if I call concat on that, concat, and then we'll pass another last in of 10, notice what it's doing here is just getting me the last value that I had, right? So there's different ways to view like the power of a semigroup. So there's parallelization because of associativity. I can divide and conquer, like say I have a big list, I can split that list in half and send each one to like say a processor or something like that, or to a different process, and asynchronously just fold those down, and then when they're both folded down, I can fold that one list down, right? So being able to concat things with this associativity gives us parallelism. The other thing it gets us is accumulation. So what we can do is just use this to our advantage, and every single time, like last, who really cares if like we're putting this over in an array, right? Like we could just get the last element of an array. Very simple, and we can do a cool thing with the maybe, so that way if there is no last element, it always returns an empty array or something along those lines. But to use this monoid to fold a list down is silly. But to use it incrementally like this or accumulatively like this, it now gives us a lot of power. So a lot of times you might be used to using monoids like with mconcat to fold a list. But you can also use them with things like pair or other bits that allow for clever usage of semigroups. You can use them to accumulate, how would you say, computations over time, right? They work very well with like stream, like if you're using most.js or things like that, you want to keep a total. All you have to do is concat two results of their stream together every time it comes down. And that'll just get you that calculation. So this is basically what we want. Instead of concating this here, we want to go ahead and use this last monoid, or this last semigroup. So we'll delete to here, and we'll just do last, actually. Instead of doing this, we'll just do last, and then bring in this value, right? So now what's going to happen is every single time that it goes through and we call chain on this pair, we're going to calculate what the one we want to pull out is, and then we're going to set that to the value of last. So when we run this chain over the pair, it's going to concat the two first elements together, and it's going to use the one that we picked as the value for that, right? So this gives us a chance to do this. We can accumulate computations on this, or values on this, using that. And we didn't have to change anything other than the semigroup that we were using. So all we really had to do was just change to that last, and instead of using last in an array or versus an array, we can keep this pretty much the same. So now let's this is going to get pretty silly, how we are going to be, you know, doing types, things like that, because we don't want to lay all this out, because really this is returning a pair which is a last of a card, and then this is on the right going to be an array of cards, and we're going to be using this pretty much for all of our deck work. Something along this lines. So what we can do here is just define something, just so it's easier for our signatures. It's not doing anything, but it's just a shorthand that'll help us as we write these comments out for the type signatures, right? So we'll consider a deck to be a pair of just what I had there, last card, and here will be a list of cards on the right. Okay, so we have a list of card there. And now we can just say that this is a deck, okay? But we're not really taking in this anymore. We're taking in a pair of integer and a deck of card, or an array of card, right? Does that make sense so far? You with me? So now we can just call this deck, basically. Now, this isn't really going to do us very well because we need this to be in a different form, right? We want to be able to chain in this computation. So every time that we call pick card, we want to provide our little Kleisli arrow bit, so that way we can chain over this pair to get our value. This isn't that. So right now we have this pair or this tuple of integer and a list of cards as the argument for this function. We need this to be curried, right? So we're just going to change this here to do this. Let's get rid of this. And this now becomes, oops, goodness gracious. This now becomes that, and oops. This now becomes that. Okay. So now this reads as, you give me an integer, I'll give you back a function that's ready to take a list of cards and then give you back a deck. So if you notice the right here, like pair, this pair or the type deck that we have or whatever, this pair itself takes on the right side, like this would be the A over here. This is where we're a functor. It takes in a deck of cards, which happens to be the parameter that runs to this and returns us a new deck, right? And card is basically, let's define card here. It's a record that has a value, which is a integer. And then we have a face, which is a string. And then we have a, what do we have? Value and face, and then we have a suit, which is a string. Okay, oops. Suit, which is a string. And we have a color, which is a string. Okay, so this is what pretty much defines that. Wow, that worked out pretty well. Well, sort of. I wonder if I can get rid of some white space there. Nope, not really. We could put it on separate lines or whatever, but this is more just for reference. So anytime we say card, we're actually meaning an object or a record that has value, face, suit, and color all in this type of shape, I guess you could say. Okay, so it's a record with that shape. All right, so now that we have pick card, what we need is to have an actual deck that we could chain this onto, right? So now, instead of this deck being this, let's just go over here so we don't need to waste any time. And we will copy all this stuff over. It's going to invalidate a lot of this right now, but that's okay. So what we want to do is have this deck actually be an initialized deck that's in the form that we're looking for, right? That is a pair that has a last on the left and an array of cards on the right. So what we'll do here is we'll just set up pair, and then we'll set up last. And this is where, hold on. So this is where it being a monoid is very important, right? So there is an empty here. So we can see what the empty looks like. Let's GG to the top, and we'll do last. Move that back up here, and last. Okay. So, that's a bummer. It requires at least one argument. So right here we'll just do last 0. That totally breaks the pattern, but whatever. So this will give you, last has an actual empty on it, right? So let's see what that looks like. Because it is a monoid, it does come with this empty function. Hey Julio, how are you, sir? And if you notice, last that is empty gives you back a last that's nothing, right? So if I were to concat this with another last, concat, this will give me my identity on this, right? So if I do my last 10 again and put that here, I get back my just 10. But if I were to take this last 10 and then concat empty on that, a last.empty, I still get back my just 10. So it gives me my identity on either side. And that's the power of a monoid, or yeah, a monoid there. So now that we know that it's a monoid, all we need to do for our empty part, since we haven't drawn anything, is just make this an empty. And now we're ready, empty. And now we're ready to concat any values or anything that we get after that, right, to it. So now we have that. We need to set up our chain function. Well, we need to get it ready to call. So this is going to be the part that we're going to chain on. So anytime that we have our pick card, we want to chain with this. So let's go ahead, and now that we have our deck giving us what we want, and this needs to be called. Oh, that would have been super embarrassing. We need to actually call that. And one of the things we can do to kind of pretty this up is do some of this and a little bit of that, and we'll put that in. And then deck is no longer an array of card. It's actually now the type of deck, which is defined here, right? So this is going to get us our deck back. So now over here, all we have to do is take our deck and then we just chain on it. So if we want to pick a card, we chain on it, and let's pick a, so we'll do pick card, and let's pick the 5th card out, right? So when we run this, we see that we get it back. So if we, now that we're still in that pair, that little bimap that we were doing before, we could still, do. So here we'll just do bimap. And it's a little different with this last because we need to actually option it out for something. So here let's just do x, and then we'll do x.option. And we want display card for that. And option and display card. And then when we option it, the reason why we're optioning it is because it does wrap that maybe. The option is available to it, and it works just like the maybe. So if we were to put something in like this, we need another function here. So this becomes that, 2 ... And we need the function for the right side, which will just map as identity because we don't really care what's there. And actually, we can check the length here, because that's going to be that list. Okay, and then this needs to go there. All right. So as we notice, our length of our array on the right is now 51. It's not 52, and we picked out the 6th card. If we wanted to pick out the 5th card or the 1st card, we could do this, and we see that our length is still now 51. If we want to pull other cards, say we want to keep pulling the 1st card, we notice that our length is now 47, and we get back our 5 of spades, which is the amount of times of doing that, right? But it doesn't matter. We can put it from there. We could do that. But look what happens when we go 99. Everything just goes straight to heck because we have a problem here. We don't have control, or we don't, how would you say, control what this index is, and if this index has overstepped its bounds like we made it do here. So this is giving us some not so savory results, as you can say. Well, there's a neat little thing that you can do. Let's just get this back to working, right? There's a neat little thing you can do. And also, let's do this. Bimap is equal to require, and let's do crocs point free bimap. And what this is going to do for us is we can now write a function like this. So we'll do const look, and we'll just call it look, why not? And then that's going to be a bimap of, and then we just take this stuff, right? Okay. We basically just want to do this, that, And then here we'll take 2DD. We'll just take this stuff and throw it up here. A little bit of magic. I like to call it pasting. And now we can just do look at M, right? Okay, and that gets us the same result. So anyway, that'll just make it easier to kind of view this so we don't have to keep that bimap and all that hanging around. Anyway, that's just a helper. We're not going to keep that around for anything. But one of the things we want to, as we noticed here, if we actually do this as 99, we're going to get our little error happen. And that's because we've extended our bounds. It doesn't know how to, this has now become undefined, and it doesn't know how to access the actual card that we're running on it on undefined because it doesn't have that, right? Well, there's a neat thing with const safe. There's a neat thing you can do with this last is if you actually provide a how would you say, a maybe to it, it's just going to wrap that maybe. It's not going to evaluate it and lift it into the maybe and do all that. It's just going to use the maybe that you hand it. And that might seem a little strange at first, but it gives us a lot of power. And how it does that is, let's go ahead and bring in this safe function. And safe is a function that takes a predicate and it takes some value. And then you give it that value, it runs that value against the predicate, and if it passes, it lifts it into a just. Otherwise, it returns a maybe or a nothing if it doesn't pass. And the predicate we want to use is defined, right? Because we're pretty much checking ranges, our boundary for our array. So that's why we'll bring in isDefined, and this comes in, that needs to be crocs, and this needs to be crocs. And we'll do predicates, and isDefined. Okay, so now isDefined, I can create something called isValid. So we'll do const isValid. And what we want to do is take safe and do isDefined. And because safe is auto-curried, it's going to give us back a function that's ready to take any value, run it through it, and either lift it into a just or give us back a nothing. So isValid takes takes any A and gives us back a maybe A. Okay? So either that A is going to be nothing or whatevs. Okay, so now check this out. If we were to take the last and we'll say we'll take isValid and let's pass in 5. So we notice we get our just 5 back. If we pass in null, we get our null back because null is still defined. The only thing we're worried about here is undefined. If we pass in undefined though, undefined, we get back a nothing. So it gives us back a last of nothing, which is basically our empty, which means it's not going to adjust anything. So if we had a card on that stack and then we go to evaluate this, that's totally cool, because it's not going to overwrite whatever was there due to the faulty bit. So it gives us a little bit of safety. So all we need to do now for this isValid so you see that we got back, in doing this, we got back our 3 of spades, and then we got back 49 is the count for the number of cards left in the deck. And if we paste it again, we see we get 48. But if I change this to, hold on. So here we have the 3 of spades and 49. If I come in here and make this 100 or 1,000, notice nothing changed. And that's because the slicing takes care of itself, and by lifting it into this isValid, if we get an invalid index or anything like that, it will still keep it the same state that it's there. So by using this last type, and because it wraps a maybe, we're able to provide a lot of safety with how we do our concatenation. And because it is a monoid, it's whatever we get a nothing back, as soon as we concat that nothing, it's going to give us identity of whatever's there. So just because of the nature of these types, we get the ability, or the nature of these algebras, we get a lot for nothing, basically. All we had to do was just lift something into a maybe, and it all took care of it for us. So, I don't know, interesting stuff. But if also you'll notice that as long as we provide an index, we're then left with a function that is that Kleisli arrow. We take an A, which in this case is a list of cards, and we get back a deck of list of cards. Well, of the last one selected, or the one that we picked. Okay? So instead of calling this pick card, I think at this time it's a really good time to change this name to draw card, because we're not really picking a card out of there, we're just drawing a card. Yeah, it looks elegant, I think. Julio said it looks elegant. And I agree, it is. It can be a little hard to read at first if you're not used to this. Oh, and actually, this is disgusting. We don't need to do any of this. Sorry, let me clean this up. Right, okay. So now let's just make sure it still works with draw card. So okay, and when we save it, we get back the same thing. So now everything's just set up. We have our normal Kleisli here, and now we can draw a card at any index, and we have bounds, like it'll take care of bounds for us. So that way, in case something goes haywire or whatever, it doesn't bring us to our knees until hopefully things get caught back up. But either way, it's not going to throw an error. Okay, so now that we have the ADTs names give additional information for free. Oh yeah, that's a good point. I never thought of that. Yeah, some of them do. Actually, that's brilliant, sir. I never even thought of that. But yeah, there is clarity in the names, as Julio was saying. So now we have the from that. So now we have everything we need with this draw card function, because remember, we're going to be using that state machine, or we're going to be using that random number generator that we created the past few times. We're going to be using that to actually give us this index value. So we're at the point now where we are ready to start reading from state. So before we start doing all that, though, there's a couple things that's we kind of need to, some debt we need to pay back, right? So I'm going to close these out real quick just for now. And if you look here, we're going to need these same functions, right? We're going to need to pluck a seed, but not pluck a seed. We're going to need to pluck the actual deck off of it. And we're also going to need to put the seed back, or put the actual deck back. So after we do all of our work on the deck, we need to write that back to the state. So basically, we would need to copy all of these over, and I don't know, that just doesn't seem very cool to me. So, and it'll be nice because if you notice, the only reference to state in here is through this get and modify, and you'll notice that the only places they're at are places that we could abstract out anyway to get the same value inside of our deck file. So with this little refactor we're about to do, we effectively take all of the hooking up of the state and all that and move it into these helpers that will just do it all for us, right? So let's first create a helpers file. So we'll create a helpers.js, and we'll just keep this in model, right? No big whoop. So here we're definitely going to need this get and modify for sure. We know for sure we're going to need that because that's where we're doing most of this stuff. So let's create a function here called getKey. Notice here how we have getSeed. Well, we really just want to get a specific key off of that, not seed. Seed is very specific for that. So what we're going to do with our getKey, it'll basically be the same sort of thing, except this is going to take a pair of string, oops, string, and it's going to take some a, any a of whatever that is, right? And the a is, of course, going to be, you notice how we have this default value here for pluck seed. We need to still provide this default value so we can pass that along and initialize it in the case that it hasn't been initialized yet. It's a fun little pattern to do with this, so we want to keep that pattern going with that, right? So that's what this a is. This is going to be the thing that actually initializes the state back to that. So now with getKey, we want to what's the other thing we need to do? So if you notice here we have, oops, where are we? So if you notice here, we're calling these functions with unit, so we're not passing anything to it. It all takes care of it all in the state and bits like that. So we're not passing anything to it, so we need to keep that same interface here. So we're going to do the same thing and pass unit, or accept unit as our second argument. It's really our third argument, but our second curried argument, I guess. I like to consider this one argument, even though it's two arguments. You can think of it as a pair of string and anything, even though those are two things you need to pass to it. But anyway, that's probably more confusing than it's worth. So the thing we need to return after this now is a state of S and A, because you'll notice that's what we get back here. So when we call getSeed, we get back a state of GameState and integer, and whatever the a is. So if you notice here, the default that we pass to this is integer. So in this case, when we implement it, this a for the getRandom, this a is speaking about that integer. But we need this to be generic because we're not always going to be working with integers. In the case of the deck, we're going to be working with that deck type. It's not going to be an integer, so we're going to need to initialize it to that deck type. And that's why we say go ahead and make this anything. That's why that a comes into play, if that makes sense. So here, all we need to do is set this up for getKey. And then getKey, like I was saying, it takes the key and then it takes the default, right? See how we have this default that we're passing along. And so from there, what do we need to do? I guess we can just move that other thing over, right? So here's going to be our unit that we're going to pass. And actually, let's just put this on the same line, because if we do that, we can pretty much copy this over, I think. So if we do get, and I guess we could substitute this, right? Yes. Yes. So then what we'll do is come into here, and get needs to take a function. All right, so let's do it this way. That is more confusing than anything, than all get out, right? So let's just create a new one. So we basically want to do get, and then we want to take this here, this whole thing, this little darling, except we don't need the def. But get needs to return a function. So this b is basically compose. And we need b and option in here. Oh, and prop. So we need all of this in here. Okay. So that will get that. The def comes into here. That becomes optioned, and then this becomes key. Right? So let's see, we take our key, we take our default, and then that's going to get us back, B of course is composition. Yeah, I think this works. So let's go ahead and take this out. Module dot exports. I think this is right. We'll see. We'll see. And then we'll just get rid of getKey. Okay, so now we can bring getKey in here, and we'll do getKey, and getKey is a require from this helpers, right? Because it's in the same directory here. So now we have that. We have that. We have B. So what we want to do is on this get seed here, all we need is to do get key and pass it in seed as our string, right? Ooh, I hope so. And then our default is, of course, this seed 0, which is the default we were providing there. Okay, so now we don't need pluck seed anymore, which means we don't need this anymore. Really cleans up this file, huh? And bada boom, bada bing. All right, so now let's just test this. We'll jump into index because we always want to test our refactors, right? So we'll open that in a new tab just so we can test it here. And this is our little workbench. So here let's just do pull random. And pull random, of course, is going to come from require model Rando. Okay, so now we have our pull random. We might as well bring in our initial state again, right? So we need initial state, const initial state. Oh, all this stuff before we test this. I should have planned this out before doing this. So here we do seed, and we'll set seed to good old 23. And here we will set our deck to be deck. Okay, so now we'll just jump down here to the bottom, and we have our pull random. So here let's just do pull random, and we will run with, because it's a state monad, run with. And what are we going to run with? We're going to run with pull random, or initial state. Okay, so get key is not a function, so this is good. This is good. And the reason why get key is not a function is because why is get key not a function? Get key takes that to that. Module dot module. Nope. Oh, wait. Okay. Interesting. Oh, I needed to save it. People should save things. Okay, so now we see that get key comes in, and we call get seed here. So it looks like just by taking that out, we're able to remove a lot of the dependencies that we brought in, right? So now we have our get seed. Our get seed just calls get key, and we say what we want to pull off, and we say what the default value should be if it's not there. And that's it. Now we don't need to worry about that anymore. So now the other part we need to move out, if you notice we have this modify that comes in here. We want to also take that out because that's something we're going to have to do with the other type as well. For deck, we're going to need to be able to modify the deck. So it'd be nice to have another function like this that could set us up like that. So we'll just create a put key, and put key is going to be a function that just takes a key. And actually, let's define this here. So we'll do put key. And put key takes a string, which is the key value that we want to put this to on the state. That takes a string, and then it's going to take some a, and then it's going to give us back a state of s and unit, right? So if we look here on our put seed, we see that's what happens. We give it an integer. Since we're not setting the key up or things like that, this is a helper that will set everything up for us. But the part we care about is here. So in this case, a is an integer, and it's going to give us back, s is the game state, it's going to give us back the unit type there. So this is what we want to match. We want to match this, but allow any type to come in to be what actually sets that key on the state. Okay? So to do this, we need to do a little more composition than what the B allows you to do, right? So the The compose B is just the B combinator, so it only will take two functions. We want the compose that will compose as many functions as we want. This is more of an optimized version whenever you only have two functions that you need. So what we really want, and we'll just keep the name the same because it's still the B combinator, right? So we will grab compose from helpers. And now that should still work. But now we need to do something a little weird, okay? So let's build our composition. The last thing we know we need to do is provide a function to modify. So we need to call modify here, but if you notice, modify takes a function. So the function it takes is this assign that has one thing partially applied to it, right? So by doing that, since assign is a binary function, it's actually going to get us back a function ready to take the next argument, which will then, get provided by modify, which will then return the result that modify will add to the seed. So we need to do kind of the same thing. So let's go ahead and bring this assign in. We will just do assign the function itself, and remember we need to partially apply it to something, right? So we'll do that with object of, because remember we have this key, and over here we're creating an object of that seed. We're basically putting that there. So what we need to do is to create an object of the provided key. So we just do that, and let's go ahead, object of, we'll bring that in. And object of is under helpers, and this is object of. Okay, so now here's what's going to happen with this. We have this function that now takes a string, and then we'll take an A. Once that A hits, which is going to be our integer, right? That's what it is here. It's an integer. As soon as our integer hits, it's going to create an object that is the key of whatever key we put in and the value of our A. And then it's going to take that and give it to the first parameter of assign, which now gives us a function that we can pass to modify. And then modify, once it's called with that function, is going to give us back the state with that function wrapped. Does that make sense? I know a lot of times, at least when I was doing this early on, when doing these point-free things, I would mostly just deal with values through here. But do you see what we're doing here? We're actually putting together and partially applying a function to something that takes a function, right? Does that make sense? I'm hoping. All right, moving on. If you got a question or anything, or that doesn't make much sense, go ahead and put something in the chat. All right. Okay, sweet. Julio's on board. If anyone else, if you got anything, it's okay to interrupt. That's what I'm here for. So now let's go ahead and put this put key out to the world and see how that works. So now we need to replace what we had here with put key. Okay, so now we have put key. What we really want to do here is change put seed to actually just take put key, kaput key, put key, and what does it take? So put key takes a key, which is seed. And that should do it. It didn't, because I didn't save it over here again. You'd think I would learn my lesson, but I don't. Okay, so now we have that put key there, and that's going to get us back the little bits. And what we need to do really though is check, because we're not playing around with that. We're not looking at that. So let's actually do an evaluate with or an execute with, so we can look at the state and make sure that it's still, execute with, that it's updating our seed. So if we notice, our seed has been updated, and it's been updated to the value that we want. It's the value that was there before. So our seed's getting updated. It looks like our little helper functions worked. So now we notice, now that we look at our linter, we get rid of this, and now look at that. everything that we have here is pretty much a JavaScript function, and we never mention state in here except through these helper functions. So this is it. This is all we brought in. It's all we require. So that cleaned up really, really nicely, if I do say so myself. So now let's just jump back into our index here. And let's see. Now that we have those, we need to be able to read and write to the deck portion of our state. So we will do that just by bringing in these helpers. So let's just copy over. I know copy paste is a horrible, horrible thing, but since we already have most of these defined here, we'll just do get and put here, right? And we'll bring this down here, throw this here, and we'll have our get seed function. Now I like to keep my functions that are dealing with the state and like things that aren't specific to this deck. I kind of like to keep them downstairs. So we now need to bring these in, and that will be get key and put key. Oops. And put key. And that will come in under helpers, right? So now we have our get key, our put key, and we want this to be, there's get seed, we want this to be get deck. Okay, and then we'll delete to here, get deck. And, boom, boom, boom. We need this to be deck, so we can pull the actual deck off of it. Notice on our state we have this deck, but we need an initial value for this. Oh, we need initial values. So let's make an empty for our actual deck. So up here is our JavaScript, and here are our deck working functions. So since we're going to work on the deck, let's do an empty deck. Okay, and an empty deck is just a deck. That's all it is. And we'll do const empty deck. And our empty deck is equal to pair last empty. Oh, don't we already have this defined? Hold on. We do not have this defined. Okay, so empty, and we want this to be an empty. It's basically calling empty on both of the types in there. So we have an empty list, and then we have our empty last, right? So now we have something that we can initialize this with, and that will be empty deck. Oh, you know what? And maybe as another refactor, empty deck. Maybe as another refactor, and let's actually make this a function. Okay, so maybe as another refactor, I like to use pointed functions instead of actual values. Just something I like to do. So now with this empty deck, another thing we could do is, since we already have this get key here and things like that, we could probably change our helpers so we don't have to build this deck portion out. Since it knows how to add it, we should just be able to set an empty deck. But I'm not going to do that right now. Right now we'll just leave it like this, maybe in a later refactor. We've already done too much refactoring for all this, right? So now let's get put deck all set up. Oops. Let's do put deck, get that all set up. And put deck is equal to put key except deck. So now we should have all of the same power that we had before. And then that's going to get us our GameState. This is actually going to get us a GameState and deck over on the right. And then put deck is going to get us our unit there. So that's all Groovy Tuesday, or Ruby Tuesdays. Groovy Tuesday? I don't know what I'm trying to say. Okay. So now we have the ability to actually pull from the deck and make changes to it and then write our deck state back up to it. Awesome. Time to take a sip of coffee. Sorry to drink in the mic, but once I position the mic, it's very hard to get the sweet spot again. I think I've already knocked it out of the sweet spot though. But okay, so now that we can get and put to the deck, that's really cool. But what we really want to be able to do is think about how we're going to get this random number out, right? So we're going to have to call this pull random function, and then that pull random is going to get us a how would you say, a floating point value on its A for state. So we'll be able, anytime we chain and all that, we're going to get a floating point value that's going to come into our chain function. So what we need to do is generate an index based on the current length of the deck, which means we're going to have to read from the state twice. We could read from it once, but then we're doing multiple transitions. It kind of makes it very imperative, right? We want to keep everything just like simple state transitions all the way through. So we don't really want to do that too much. We don't want to pull from it once. We kind of want to take each one of these as a separate transition through the state machine as we're doing it. Okay? So now that we have our deck access in place, let's start thinking about the JavaScript functions that we would use to do this. Let's not think about like the state or things like that at this point. Let's just take it down to the simple JavaScript, and we'll start doing our stuff here. So the first thing we need to do is limit it, right? So we need to take a floating point value. So let's call this limit2. Okay. So we need to take a float, and then we also then need to take the limit or the length of the deck, right? So we'll call that an integer, and we want to return another integer, which is a value in between 0 and the length minus 1. That's what we want to limit it to. So basically, if you can think of how we're doing our, how would you say, how we're doing our random number from a 0 to 1, we're actually creating a normalization of that original integer in a limited, we're basically doing a normalize there. So now we need to scale that. We need to take that 0 to 1 value, or 0 to 100%, depending on how you're doing it, and get the percentage based on that limit. Basically, we don't want anything that will exceed our index. So what we're going to do is we'll create a function called limit2, as it's defined up there, and that's defined as, we'll just take our random number, and after our random number we'll take what our limit is. Okay? So now if you think about this, all we really need to do is multiply this to get a percentage of, like, because this is going to get us a number from 0 to 1. So we want to multiply that by our limit, and then that's going to get us a percent, or it'll scale down that percentage to a specific index in our bits inside of our array. Now, this is going to get us back a floating point value. We don't want that. So we're just going to do a bitwise OR against 0, which will basically make sure that we get back a 32-bit integer. What we could have done is did a math.floor here and gotten the same results. Math.floor like that. But I don't know. There's no reason to do all that. So we can bring this in. This is a random number. And now watch, if we have a random number, so if we jump down here and let's do limit2, let's just give this a spin. We'll take 0.467, whatever that is, and then we will limit it to 5, right? So we get 2 back. And it picks a value, so even if I were to do 1, watch, if I do 1, or 0.999 like that, it should get me back 4. If I were to do 1, it gets me back 5. So, and we get a value from 0 to 1, not including 1. So we don't ever have to worry about it extending that. It goes from 0 to just below 1. So we're good there. So now if we do like 50%, basically we're just seeing what the nearest 50% is and cutting off the remainder, basically. And that's all we need to do to keep it within there. So anyway, now we have this cool function, limit2, that if we provided a float and then provided a limit, we can do this calculation and it'll get us a value in between that, right? So the next thing we need to do, and let's jump down here because this is an actual dec function, something that works on decs, something that doesn't work in normal JavaScript. So we're going to be inside of our type for this. So we're going to call this dec length, okay? And this is what's going to get the length of our dec. And what's left. So this function will take a dec and then return an integer, right? So this is your basic reduction function. We're just going to go from an m of a or an m to some other value, in this case an integer. All right, so let's implement this. This will be const dec. And the thing that's cool about these functions is they work with extend, but don't worry about that. Well, maybe we'll worry about that. I'll show you what that looks like. SND, and then we'll just grab the length of that, right? So because this is a pair, let's go and look back at our type here for dec. Because this is a pair, and if we call it's on the left side or the first, it's actually our selected monoid of card, the one we selected last. And then on the right side, which is the second, or SND in this case, that's actually the array of cards. So that's the part that we want to get the length of and see what's left there to select from. So by doing this, we'll do dec length is equal to, and then this will take a dec and a little bit of this and a little bit of that. Oops. And we'll replace this with that. So now we have a dec length. So we can pass this length. So if we have our dec or whatever, we can now do dec length. Where did I misspell it in the signature? Okay, I'll have to fix that. So we can do a dec length and we'll just pass in dec. And so now it's 52. We could take our dec length after pulling those 3 cards from it. So since m is going to be a dec, notice it just gives us the length of how many cards we have left. So we have 49 cards left. So we got the first part, or I would say the second part to this. We got the part that matters for our limit to. This is our limit. Now if you look at this, notice this limit has to do with the dec itself. But this outer part, this random number, actually comes from the state, right? So this right here, this limit function is something that we could use to map over to actually get the dec length over the dec itself, and then that will move it over into the right. So now we have everything we need to actually use our initial state here. So let us create the last function that we need, and this will be our first state function. So this will be the one that actually works on the state with us. We will call this getLength. Okay. Now getLength, and I'm trying, the naming on this is probably a little bad, but I don't know. We'll go back and fix that as better names kind of come to mind. So we see here that with getLength, we want to take a function that takes the unit and then maps that unit. It's basically, it points to a specific state. It maps that unit to a GameState of integer because we want to grab that integer. So to do this, we need to pull dec off of the state and then map our function over it, right? So let's do that, I guess. Const getLength. And from here, getLength is defined as a function that takes unit. And then here we can just call getDec, right? And actually, let's make this a little prettier because we're going to be chaining on that a little bit. So we have getDec, or I'm sorry, getLength, and then what we do with this is we do getDec, and then we want to map over that because at this point, whenever the value that's going to be passed to our map on the right is going to be the deck itself. So now we take our deck function, which was deck length, because this is the one that takes a deck to an integer. We need to pull deck off, and we'll do deck length. Give that a save. And then here with our M, actually, now we don't need to do any of this. Now we have our first ability to jump into our actual state here, right? So what we'll do with M is we will do, what was it, get length. Okay. And here we'll just do M dot run with, because now this is going to return a state monad. We're going to do run with, and we'll just pass in our initial state. And if you notice over on the, if we do an eval with, because this is an evaluation, we get back 52 because that's how many that we had, right? That's the length of the deck of cards because we haven't done anything to it. But this is now wrapped and we've already hooked it up to the state monad. So it is actually using the deck that we passed into this initial state. And that's it. That's all we had to do to hook that portion up to the state monad. A lot of this other stuff we'd have to do anyway. It's basically just using these functions here, the get deck and put deck, that will automatically do all of the hookup that we need to work with the state monad, right? Okay, so now that we have the length and all of that, we need to actually limit this, okay? So what we do for the limit, and let's just go ahead and we'll start building out what I like to call a pick random function, okay? So we'll call this pick random, and we'll do pick random. And pick random's defined as a function that goes from unit to a state of GameState, but now we want our integer. So that way we can pick our random integer. Like we'll use these limit functions, that limit bit that we've created and all that, and we just return back our integer. So we'll go GameState and an int for our a value. Oops, not an int1. I know it seems classy. So then we do pick random is equal to a function, and let's do this. And this will be pull random. So remember we had pull random that came in from our Rando here. So if we look here on Rando, we have pull random, and this is what actually generates our random number for us. So this right here is going to take care of updating the seed and doing all of that. But when we go to use it, all we're going to do is just call it, and it's going to already have had the seed updated, and it's going to have the random number in the A ready for us to use it, right? So let's see what that looks like. So here we'll just do pick random, okay? And actually we don't need this M anymore. We'll just do pick random, and here we will do that, okay? So as you see, once we actually call the function, we get back, and this is our random value that we got back from our random number generator. Notice every time we save it, it's the same number because we're using a pure random number generator and updating that seed every time. So, I mean, we could just chain in another pick random, right? Just so you can see that it still works the way that we expect it to work. See, we got a new random value, but it's the same random value of calling that twice, right? So it still works. We still have our pull random. But now we want to create a function here. Since we have this random number that will be a float, we have this function limit2, which actually takes a float and then an integer and then an integer, right? So to do this, all we should need to do to pull random or to pick random, well, actually, we need a way to move from a floating value into, okay, so we need, what should we call this? So we'll call this next thing that we're going to build limit. So what we need to do now is hook up this other value to it, because we're going to need to do 2 chains or 2 transitions to get this. One transition is going to get us our random number, and that's what this one's going to be. This is going to get us our random number, and then we need to do another transition once we have that random number to actually pull the length. And then from there, we want to map and do our limit2 that we have up here, limit2. We then want to map this limit2, passing in our random number, and then once we do the map, that's going to apply the limit to here and get us our value back. So it sounds confusing, but let's try to put it together so it's less confusing. Okay, so here we have our limit, and limit is going to take a float, and it's going to get us back a state of GameState int. Okay, so now that we have our state of GameState lint, or int lint, let's create limit. And limit is, like I said, going to take our random number, right? It's going to take our random number, and then we want to get the length. Because remember, we have our random number now. We now need to get the length. So we can call, do we have get length? Yes, we do. And get length is, as we see here, going to return us a state monad that has the game state plus the integer that we want on the A. So since that integer is on the A, all we should have to do is map with limit2. Okay? So now, make sure there's no errors. When we do this, all we have to do is chain on this limit. And we get a function back. Why? Because limit2 needs this random number applied to it. So now we get 42. And it's within the bounds of our array. Right? So now we have pick random, and basically that pulls a random, which gets us our floating point value. That floating point value gets passed into, when we call this chain, it's going to get passed into this limit function, which is here. Then we're going to return a new state monad that's going to, whenever it runs, it's going to pull the length by calling this get length here. And then we're going to map that limit2 over the Rn partially applied here. And that's going to get us our random number of 42. So if we were to actually change this seed, we would get, of course, different values. Like we can make this date.now, and we'll see that every time we do this, we get a new value within the limits of our bits there, right? And it never goes above 51. But we're doing that because it's all pure. Yeah, the reason why it's not pure is, or for us, why we're getting new things every now and every single time, is because we're initializing it with a different seed. But we would be able to get the same seed each time. All right, so we're still going to keep this look around. So I guess the next thing we need to do, oh, this needs to be draw a card. Okay, and this length, there we go. That's better. All right, so now we're back to 42. And if you start with 23, do our evaluation on a 52 card deck, that's always going to go to 42. So that's pretty neat how 24 will always map to 42 whenever we set it up this way. Okay, so I know I went over this super duper fast, super duper quick. Before we move on to the next point, though, where we're actually going to use this random number to draw a card, Are there any questions? Is there anything that you want explained? Talk now, forever hold your peace. Well, you can always do it in a comment later too. Or if you want to hit me up on like Gitter or something, you can do that too. Really? You guys are much better than me. It took me like a year to like figure this stuff out, and it seems to be clicking all for you. And I'm not, I mean, it's taken me a year, but I'm not even that good at it, right? We all good? All right. Okay, moving on. Feel free to interrupt, though. For the people that just showed up, if nothing is making sense, go ahead and interrupt. If you're late to the party, that's fine too. And you're curious what's going on, if you got a question, feel free. How does a pure random work? Totally. See, I can answer that. It's not pure. You can't have a pure random. Just like if you were to have a random, math.random. So the reason why math.random isn't pure is because we don't own the seed to that. The algorithm that it uses, if I provide the seed to it, I will always get back the same sequence of numbers, always for the same seed. But we don't own the seed for that. So what we did, and if you go back and look a couple episodes, we actually created the pure random number generator, pseudo-random number generator, I should say. Yeah, well, that entropy will come from this initial state, right? However we decide to do it. Right now, I'm saying it's pure because it'll always work with that, right? So even though this isn't a good source of entropy, if we initialize everything with date.now, we will get different numbers every single time, right? And we could do other things, like maybe if we're keeping track of, how would you say, keyboard strokes, maybe we do a checksum every time they move their mouse. We take from position to position and just keep doing a checksum on that. We can then OR in that checksum, and that'll get us the new seed. So it's pure because we own the seed, and no matter what we send to it, it'll always give us back the same result. Whenever we run this, it's not going to be the same result every time. That would be a very boring game, right? It'd be a super boring game. So, yeah. So that's what I mean by a pure random number generator. But now everything here we own. Like we will always get, I can play a game back if I know that initial seed and like keep track of their actions of how they bet on their card guesses and things like that. Then I could play back their exact game as long as I know that first seed. And that's because we're using the pure random number generator. Pseudo random number generator. So, yeah, and if you guys are curious about that, yes, so it's controlled. So the impureness is controlled at the edge, right? So this is that edge that people are always talking about, this initial state, that we're going to have to call run with some initial state. So if you notice here, we're calling eval with, run with, and all that. This is the edge for this state monad. And that's where we're allowed to do our impure things like read user input and things like that. But everything inside of our model, up until we call eval with, is pure because it'll always give the same result for every value that we put in. Or that's the goal anyway. So does that make sense, Julio? Did I second your point with the impureness is trapped? Okay. Yeah, if you got any questions, feel free to stop. Okay, so now that we have that, this isn't really going to do us too much, right? Awesome, cool, I'm glad I could help. Or I'm glad I could explain it. We don't really, do we need this open? We don't really need this open anymore. Pfft, we're pretty much going to replace all of that with this, okay? And now we're kind of at the finale part, like, the only reason we built all of these functions, and if you'll notice with the the way this is structured, we have these functions here, which are JavaScript functions, right? This one, we're lifting into a maybe and all that, but really we're whatever. It's still kind of JavaScripty. It doesn't have to do with the deck. These are things we're going to map or use with them, right? Here we have a function that goes from a unit to a deck, and that'll get us an empty deck. Okay? And then here we have a function that'll get us, these are the functions that start working on the decks themselves. So this will work on the deck type. Here we have a function that will take the length. Here, these are things that know about how a deck operates, right? These are what we would lift our other functions in. This is how we draw a card in this structure that we've created. And then here, this is how we, these are our state functions. This is how we interact with our overall state monad. So we have our getDeck and putDeck, which are our helpers for accessing. And these are basically our access helpers for the state. And then this is the stuff that actually does the state transitions. These are our state transition functions. So we have pick random, we have limit, and we have get length. We also have, yeah. Anyway, those are our transitions that we're going to use. Okay. So now we need a way to pick a random card. Okay, so to do this, we have this function here, and where is it? Draw card. So you see this draw card here? This actually takes an array of cards, right? It takes an array of cards. It doesn't take a deck. This is made to, it returns a deck. But this right here was made to be chained in. We made this to chain in with a deck. Well, we have a little interface mismatch here because all of these functions so far have been working with the deck as a whole. So we're going to need one more function here. We're going to call this one pick card. So this will be our pick card. Okay? Maybe we'll call it pick card at or something. Or maybe we should call this draw card at. Yeah, let's do that. This hasn't been used anywhere yet. So we'll call this draw card at, and here we'll call this draw card. Okay? All right, so we'll define draw card. We need an index, right? Here. But we want it to return us a state of GameState. And here we want it to we're going to modify whatever that thing is, right? So we're going to pull the card out. We'll have this actually do all the interactions to our state for us. This will be our one transition to actually draw the card at that point in time. Okay, so now we have our draw card, and then draw card is defined as draw card. There we go. Draw card is defined as it takes an index. So notice how we have this integer here. So we need to take an index. And then from there, we need to return a state. Obviously, since our A in this case is a unit type, we're going to be doing that modify like we've done before. So we're going to be using this put deck, obviously. See how the put deck is going to give us that state? So we know we're going to be doing we're going to have to do a put here, or well, a put deck after we're done doing all that, right? So we need to get the deck itself because we have to get the deck to actually modify it. So we can call getDeck, and then that's of course going to pull the deck off of there, and it's going to move it into the A. So now that we're in the A, we want to map on that. So we want to take draw card, or what is it, draw card at, and then we want to pass in the actual index that we got here, right? So this is where we need the index. And that's where that index comes in. This is the index that we're actually getting from this draw card function, right? We need to pass it down to draw card at. But there's a problem here. The thing that we're going to get back is not going to be the actual bit that we're working with. It's going to be the whole deck. We need this function to actually get us back, or to give us an array of cards. So basically, since this was used or is needed to be chained in, we need to basically, how we were using it earlier, is actually chain this other function on it, so that way we get a new modified pair. So to do that, all we're going to do is just bring in a point-free chain, so that way we don't have to like do a chain, take that, call dot chain inside of our chain, and then hook the function up that way. It'll clean up real nicely with the point-free chain here. So here we'll just do point-free, and then we'll do good old chain. How are we on time? Oh, this should be perfect. I thought this one was going to take a long time, but it didn't. Okay, well, I mean, it did, but not as long as before. So what we're going to do here is then do chain, and that will take the deck that's there and then call chain on it with this function. So we're basically using it the same way that we used it when we originally built it, because this map on getDeck is going to return us a deck. So now we're going to take that deck and chain our drawCard now that we have an index that we can actually apply to it. What? So now all this means, and remember that index is coming from here. So all we need to do now that we have that is do drawCard. And we get our cards. So let's go ahead and put our m back in here so you can kind of see what's going on. We'll do const m, or game is equal to, and then we'll do pick random. Okay. Okay. And we'll do eval with here. Why not? And then here we'll do m. We don't want eval with, we want execute with. Okay, and then here we'll take game dot deck and then look, right? Well, that's not good news. What's going on there? Okay, so now we'll do drawCard. Oh, did we not put? That's right. I'm so sorry. Because now we need to chain in put deck. Sorry about that. So, and this should work? Yep. All right. So what happened there is now when we do this drawCard, we need to update whatever the deck was by doing this chain, and then we need to take the result of that and push that over and update the state. So that way the deck gets updated, right? So if you look here, we have pick random, and if we call it once, and then here we'll just dot chain pick random in, and get rid of this. See how we get another one? And it keeps decreasing. So now we can randomly pick a card. That's it. That's all I got. Does that make sense? Anything? Any questions or anything at all? Okay. Well, this is it. Like, this is what we need for our deck. And now we have pretty much all the game logic there as far as we need to randomly select a call or a card. Now we can do that, and we have complete control over our state. So let's go ahead and get rid of some of this junk, right? So all of this, or most of this, is going to be moved over into our new deck file, or into deck. So the things we want to keep around in deck are values. We want to keep this deck that we just made. Let's go ahead and bring empty deck in. Okay, so we'll grab this, and now we have an empty deck there. Okay. What else do we need? We want display card, but these are all JavaScript functions. So let's move this stuff up here. Okay. I mean, they have to do with card and things like that. Oh, well, these are all card functions. So let's move them here. Okay. Because they're just basically ways to work on cards. All right, so now we have empty deck syndrome. What should we do there? We want to bring isValid in and limit to. So these should go with our normal JavaScript functions. So let's bring these in, and we'll just throw these up here. We need to bring safe and defined in, and isDefined. So let's bring safe in, QRS. And isDefined begins with I, so we'll bring that in. Okay, so we have isValid. Oh, goodness gracious, excuse me. We have that, we have that. Now, deck length, this has to do with decks. So we can come down here. This pick card no longer works for us, Captain Picard, to make that joke again. And we're not shuffling decks anymore. It's kind of not our thing. We're really not into that sort of stuff anymore. So we still want this stuff exposed. All right, so we have deck length. We have empty deck syndrome. This draw card at. So this can go here. Does it depend on anything else? Yeah. So there's our draw card at. This is set up to work with the deck. So yeah, that should go there. And actually, we could probably move that here. Okay. Since that's a little more important than the other one. And then, what is the next bit that we need to move over? These right here are our accessors. So that's pretty much all of the stuff that we needed for just working on decks. Now we need the stuff to start working on state. So here we need our get key and put key. So this can go upstairs at the top here. Oh, looks like we don't need... And we might need chain later. Let's see. Get length is a state function. So let's put that here. Okay. Anything? Oh, we don't need this anymore. So that can go bye-bye. Okay. What else can go bye-bye? So now we have our limit. And that can just go into here, since that is also a state function. And now we have draw card, and we can just take pick random. Okay. Okay. And that should do it. So the only thing we need is pick random exposed. Really. All right, so now we don't need chain here, and we need pick random. Don't need pull random anymore, but we do need that up here. Okay, so there's pull random. We don't need reduce anymore. We're probably still going to get, oh, modal helpers. So this needs to be, or model. There we go. Okay, so now we are cooking with gas. Now the only thing that we have left here are just helper functions. And all of our stuff for picking the random has just been moved down into or exported from here. And we are good. So we'll give that a save, clean this up a little bit, just so it's easy to read. We'll do some of this, a whole bunch of that, and that there. Okay, looking good. Would it be too hard to implement the history with the writer monad? Not really at all. The state history. No, not really. We could even do it with a pair, but yeah, we could do it with a pair that has a, you don't need a full-on writer for that. It's real simple. And really you don't, there's many ways you could do that. So, but that's actually really good idea, Julio, because what I want to do is, like for instance, right now we're not keeping track of discarded cards, but I'm going to be adding features to this. Like when we get this all built out and actually get an MVP working with the front end, I'm going to just keep adding features like you would see in real life. Like your manager would come to you and say, oh, we need this, that, and the other. So that way we can also look at how you maintain code like this. Right now, this is the easy part. We're putting it together and just putting it together in production. The real test for this functional code comes down to when you have changes that happen, right? So it's one thing to make this in production, but it's a whole other way to think of this whenever you need to maintain this code. So that is actually, that may be a feature. If you don't mind, Julio, I'm going to steal that from you. You'll get total credit, I promise. I'll even put you as the stakeholder on the card. But we'll implement the ability to replay a game. And I'll make sure that we get that in there so you can see what that looks like. It's not really that hard at all. Or if you want, you could pull this repo down as soon as it's there and you can start playing with it. So actually let me, we now need to, let's see here, we did all kinds of stuff. So let's do get create branch and we'll base it off ADTs and we'll do ADTs-05. Okay, so now let's do get add intent to add because we added a file. And we'll do intent to add that, and we'll do a get add -p. So these are all the changes that we made here. Yep, that's a good way to keep our workbench, I guess. This is all the changes that we made to the deck file, or the first section of them, the first bit of them. So yes, and it looks like that. Oh, is that linting? We got a lint problem here. Let's see where that lint problem is. I don't see where that lint problem is, and it's making me sad. Doesn't say. Oh, there it is. Okay. So let's quit and then start that again. Okay. Okay. Julio said, haha, cool. That would be fun. I've been looking at Crocs lately. Nice job with that. Oh, thanks. Yeah, Crocs has been fun. It's been a real learning experience. Like there's certain things that I notice that would be super great. Like for instance, pulling a value from something or, never mind. I want to be able to, never mind. These are all just ideas that I have. I don't know if any of them are going to be real, so I don't want to get anyone's hopes up. Let's see. So these are the rest of the changes. Let's just bring in our deck. So we did add a significant amount of code to this, but we oh, there's a issue right there. You see that? We have, it's this right here. We don't want that. That's bad news bears. All right, so let's quit that again, and we will keep going. And let's just review this real quick. Get deck, put deck, GameState. Okay, and yes, we'll stage that hunka burn-in functional programming. This is our helpers functions that we added, and this is how we cleaned up Rando. So Rando, we actually cleaned up a lot with those helpers, so that's pretty awesome. All right, so GST, and then we'll git commit m, and we'll do add code for session 5. Boom. Okay, so I just need to update the, how would you say, I just need to update the README on this to point to the videos and things like that. But hopefully tonight or tomorrow, then this ADTs 5 branch will be available on the GitHub repo. So that's all I got today, peeps, my fellow dev friends. I hope it was helpful today. I tried to go really quick through it. I mean, there was a lot that we did today. So if you got lost, or if you have any feedback on ways I can better present this information, please let me know. I'm not really doing it for my own benefit. Well, it is kind of. I want everybody to code this way so I can code that way. But for people that are interested and actually want to learn this or know it and want to help other people learn, I really would like some of your feedback, just so I can make it better. I'm going to keep doing these, so we might as well make it to where I'm doing it to what you guys want, or what you think is best, or you people want, or what you devs think is best. So if you have any criticism, no matter how horrible you think it is, or mean-spirited, or whatever, I'm okay with it. I can usually find gold in a pile of trash, so feel free to give me any criticism that comes to mind. But that's all I have. Next week, we're going to start working on the scoring and things like that. Oh, good. I'm glad. Oh, by the way, Northwest Calvink. Are you in the Pacific Northwest? Are you up here in like the Portland area, or up in Seattle? Like, where are you at? What's the NW mean? Does that mean Northwest? Are you up in Canada, maybe? Anyway, that person that just commented, he's doing a lot of really good JavaScript videos. I really like his flow and things, but check him out. It's I'll link to him in this, but it's Northwest or NW Calvink. So that was just a lucky guess on my part, huh? So you're in BC. Sweet. Yeah, I have a couple Canadian friends up in BC. Really good place. Really cool people. I like the people there. They're very nice so far. The ones that I've met anyway. But anyway, I hope you guys have a wonderful, or guys or gals and wonderful developers, I hope you have a wonderful weekend, and thanks for stopping by. I will talk to you later.